Howdy, Brian Vikings. We're here to talk about a new unit called stoichiometry. Now, stoich means the amount, and then metry or meter means measure. So you're measuring the amount. This is going to be all about unit conversions, and we're just finding the amounts of substances in a chemical reaction. So first, let's start off with the mole ratio in the mass-to-mass stoichiometry. Here we go. So a mole calculations. Now, before we begin, please, if you can print off these notes and follow along with me, that's great. If not, you need to learn how to take your own notes. So get a piece of paper out and a pencil, follow along with me, write them down as I'm writing them down, and then what's also important is that you write down the question. Now, you can paraphrase the question, or you're given an equation here, and you can just put the amounts over the equation. What that's doing is that's just a future note to your future self, so your notes make more sense later. So just a little note-taking skill. So first off, we're going to first identify what a mole ratio is. So a mole ratio is a conversion factor. Hey, we've seen that before. That allows us to convert from a given amount of reactant or product to the desired quantity. Mole ratios are derived from the balanced chemical equation. So let's go ahead and think. The balanced chemical equation, they are actually going to be the coefficients in that chemical equation. So let's think about one little example here, and we want to be thinking about in particle diagrams. So we have nitrogen reacts with hydrogen to make ammonia, and so there's there's one nitrogen molecule, right? Even though there's two atoms, that's one molecule. We'll zoom in just a little, and then it's going to react with three hydrogens. So three hydrogen molecules, so that's 6 total atoms, and that's hydrogen. And then it produces 2 ammonia molecules. So it makes ammonia. Let's do 2 nitrogens there. And then each one is surrounded by 3 hydrogens. It's even got the correct geometry. So look at that. So that is our ammonia. We'll just write NH3. Okay, so much for color coding. But as you can tell, one molecule of nitrogen reacted with 3 molecules of hydrogen to make 2 molecules of NH3. That's what those coefficients mean. Now, so if we scaled it up, let's say if we had 2 molecules of nitrogen, we would need 6 molecules of hydrogen and 4, and that would make 4 molecules of ammonia. If we had 1 mole of nitrogen, we need 3 moles of hydrogen and 2 moles, and we would produce 2 moles of ammonia. You see, you could scale it up. It's always in that same ratio, right? So that's what a mole ratio is. So mole ratio is can be written as a fraction as well. So 1 mole of nitrogen to every 3 moles of hydrogen. You could have another mole ratio of 1 mole of nitrogen to every 2 moles of NH3 is produced, right? And let's just do one more. We could have 3 moles of hydrogen for every 2 moles of NH3 produced. Okay, you could do more. You could do 2 to 1. You could do 2 to 3. You could do, but we'll just show you those 3. So essentially, you're just looking at the coefficients. That's all the mole ratio is. That's the real key here. That's the only really big thing that's new and added to this whole unit. After that, we're just going to use that same thing as a tool. So in a mole ratio calculations, you will calculate the number of moles of one substance that will react or be produced from a given number of moles of another substance. So you're going to be given moles, you could be given moles of something, and you could calculate moles of another substance. It just requires one step conversion using a mole-to-mole ratio. So for example, let's do number 1. How many moles of oxygen are produced when 3.2 moles of potassium chlorate decomposes? The other product is potassium chloride. So we'll have to make a chemical equation off of this, and that's why I taught you that in the last unit. It says that potassium chlorate decomposes. 3.2 moles of potassium chlorate decomposes. So I know that that is potassium chlorate. I know that that's chlorate because I look at that periodic table. That's a ClO3 with that minus charge. And so I know it decomposes, so that means that there's only one thing on the left side, and there must be some things over here. Well, I know that there's oxygen here. That's actually what I'm looking for. So I know that there's oxygen over on the right side, and it says the other product is potassium chloride, so that's KCl. Simple enough. So now I just need to balance my equations. So because there are 3 and 2, that's not balanced. So if you have a 3 and a 2, the magic number is going to be 6. So make this a 6 by adding a 2, and make this a 6 by adding a 3. Okay? So now there's 2 potassiums, 2 chlorines, so I need to put a 2 here. It's a balanced chemical equation. You must be balanced for this to work. Now, so here we go. We were started with 3.2 moles of potassium chlorate, KClO3, and it decomposes. And so we want to know the moles of oxygen. So we're just going to multiply by that mole ratio. This time we're going to put moles of potassium chlorate. And this is where it's important to actually put the substance. And then we're going to put moles of oxygen on top. Okay? And so we have a moles over moles. All right? When that happens, we use the coefficients in the equation. So the moles of oxygen is 3, and the moles of ClO3 is 2. It's a 3 to 2 ratio. So that means that these are going to cancel out, and we're going to end up with moles of O2 at the end. And so 3.2 times 3 divided by 2 equals 4.8 moles of O2. So that's what you would be able to type in your calculator. You would type that in your calculator easy. You only have to hit enter once. 3.2 times 3 divided by 2. Okay, let's try the next one. Let's go a little faster. Why don't you pause and try it, and then come back. Okay, welcome back. How many moles of water? So remember that this 4 comes from here, and this 1 comes from here. The coefficient is 1 in that case. So 15 times 4 is going to be 60. 60.0 moles of H2O. Hey, notice those sig figs right there? It's I started with 3 sig figs, and I'm going to end with 3. Even though these are considered exact numbers, so they have an infinite number of sig figs, so we're not going to consider those. Okay, you just look at the ones you start with and the ones you end with. So let's throw one wrinkle into the system, and let's do something with mass. So let's if we're given mass, could we still do the same problem? Yes, we would just have to do one extra step. Okay, so it says what mass of nitrogen? Okay, so we're looking for grams. That's the unit, right? Will require to produce 35 moles of ammonia. So if you notice, we were given this, but we need to find out something of another substance. This is exactly what the whole unit is about. Is you're giving something and you're trying to find the mass or the amount of something else that reacted. Okay, so We just start with 35.0 grams of ammonia. I'm sorry, moles of ammonia. I apologize. And then we need to change moles of ammonia into moles of nitrogen. You're allowed to do that. You're allowed to change moles of one substance into moles of another substance. So that means that I have, and so it's a mole ratio. So I'm going to have to go to the coefficients in the equation. That's the coefficient of ammonia is 2. The coefficient of nitrogen is 1. And then I'm going, I have moles of ammonia, but I want mass. So I'm going to go one more step. I'm going to convert moles of nitrogen into grams of nitrogen. Now G stands for go to the periodic table. So we go to the periodic table for nitrogen. And so there we go. That's 14. So one nitrogen atom is 14, but this is a nitrogen molecule. So it's 14 plus 14. So that's going to be 28 grams per mole. And so now your calculator work is, again, going to be 35. Just type in 35 divided by 2 times 28 and hit the equal sign. All right? And then that's going to give you 490 grams of ammonia. Grams of nitrogen. Sorry. We started with 3 sig figs here. Let's end with 3. So that's 1, 2, and this one's not significant yet. So let's make it significant by adding a decimal place. Okay? All right. Hopefully that made sense. The rules are basically you're allowed to change one thing at a time. You're allowed to change substance here, but we didn't change the unit. And then we changed the unit, but we didn't change the substance. Okay? You're not allowed to go from moles of ammonia to grams of nitrogen. That's not going to happen. You can only change a unit or a substance. You can't change both. So hydrazine, N2 plus H4 is used as rocket fuel. Reacting with oxygen, it produces nitrogen and water. What mass of oxygen is needed to burn 100 moles of hydrazine? So let's start with an equation. So we have N2H4, and it reacts with oxygen. So let's add O2, and then it produces nitrogen and water, and that's not balanced. So let's go ahead and see that there are 2 nitrogens there. That's fine. That's 4 nitrogens. So 4 hydrogens. Put a 2 there. Does that balance? Yes, it does. Okay, good. So we want to know the mass of oxygen, the grams of oxygen here, and we're given 100 moles of hydrazine, 100.0 moles of hydrazine. And so we'll have to convert moles of hydrazine into moles of our oxygen. Remember, you're only allowed to change the substance. And we'll use the mole ratio here. And so that is a 1-to-1 ratio because the coefficients of each one are 1. And then we can change moles of oxygen into grams of oxygen. And G stands for go to the periodic table. That means that we can look at oxygen. There are 16, right? 16 grams in a mole for an atom. So now this is the molecule, so we're going to multiply by 2. So that's 32 grams of oxygen is in 1 mole. All right? And then, so that's 100 times 32. So that's 3200. 3200 with a decimal place to make it significant, grams of O2. All right? So just a reminder, where did I get these numbers? They came from the coefficients. The mole ratio comes from the coefficients, and the grams to moles, that comes from the periodic table. All right. So let's keep moving on. Now, if we're given a mass, could we do the same thing? Essentially, yes, we could. How many moles of hydrogen gas are produced if 56.7 grams of sodium are added to water? It gave us the equation. We want to know how many moles of hydrogen gas. Notice how I like to underline what I know and circle what I don't know. That's a good habit to help you identify where you're going to start and where you're going to end up. Okay? So I'm going to take 56.7 grams of sodium and then convert grams of sodium into moles of sodium, because grams are not useful in chemistry, only moles are. And so I look at sodium on that periodic table, and sodium is 23 grams per mole. We're rounding, by the way, that's fine. 23 grams per mole. And so now that if we stop there, it would tell us how many moles of nitrogen, moles of sodium. And so then we could change moles of sodium into moles of hydrogen gas. So hydrogen gas is H2. The coefficient for hydrogen is going to be 1, and the coefficient for sodium is 2. Again, I got that number from there. I got this number from there. Okay? That's it. We're done. Because we ended up where what we circled, moles of hydrogen. That's where we are. So essentially, you're just going to keep going until you stop, basically, until you get to where you need to go. So you're going to take 57, you're going to divide by 23, and you're going to divide by 2, and you're going to hit the equal sign, and you're going to get 1.23 moles of H2. Okay, make sure you put the unit in that substance at the end. Keeping the substances in your work is absolutely critical. Okay, you probably can't see it too much. It's zoomed in too much. All right, so go ahead and stop and try this next one. Okay, welcome back. That is what we got. And hopefully everything worked smoothly for you guys. If you are having trouble doing these, you need to come see me for tutorials now, because this is exactly what we'll keep on doing over and over again. So you've got to come see me if you're having trouble. All right. Now, the last little bit, we need to add one more step. So what if we're given mass and we want to find out mass? Well, we're just going to have to add one more conversion factor in there. Okay? So this is what we'll do the most frequently, where you'll start with the grams of a substance. We'll just call it A. And you're going to have to convert it into moles of your substance, A, right? We're not changing the substance yet. And then you're going to change into a new substance using that mole ratio. And then you're going to change from that moles of the new substance to moles of, to grams of the new substance. Okay? So, to change from grams into moles, you'll use that periodic table. And to change from moles into moles, you'll use the mole ratio. That's from the equation, okay, the chemical equation. And then from moles into grams, again, you'll use the periodic table. Okay. Now, all right. So what mass of oxygen is needed to completely burn 137.9 grams of butane, C4H10? So here's your butane. you have 137.9 grams. We want to know the mass of oxygen. What mass of oxygen is needed? To get rid of all the butane, how much oxygen am I going to have to add? That's what we're asking. We're calculating that perfect ratio to get it that's needed. So this can be used to economically figure out how much you need for an experiment. You can calculate it. So that's why we use it. So if you have 137.9 grams of butane, and we're going to shift over here, this is our grams of our A, and we're going to change into moles of our A right here. So we're going to change into grams of butane into moles of butane. C4H10. Okay? So we'll have to go to the periodic table here. And so we know that carbon and hydrogen, here's carbon, that is a 12, and then hydrogen is a 1. Hopefully you memorized that by now. So 4 times 12 plus 10 times 1 is going to be 58. 58 grams per 1 mole. And now we're going to change from moles of our substance of butane into moles of our oxygen. So again, we're going to put moles of butane on bottom so that it cancels out. And we're going to put moles of oxygen on top so that's what we want to get. And so now we have to use the coefficients in the equation. The coefficient for butane is 2, and the coefficient for oxygen is 13. And then we're going to change moles of our oxygen into grams of oxygen. So moles of O2 into grams of O2. So now we established earlier that the molar mass of O2 was 32 grams per mole. That came from the periodic table. And so our calculator work is going to be 137.9. And we're going to divide by 58. We're going to multiply by 13, that 13. And since 2 is on bottom, we're going to divide by 2. And since 32 is on top, we're going to multiply by 32. Notice how I'm just dividing by everything that's on bottom and multiplying by everything on top. Hit the equal sign, and you're going to get 494.5 grams of O2. Okay. Remember, this number came from here, and this number came from here. Okay. All right. Try that last one on your own, and we're going to be done. Okay, one little tactic that some people do, and that's the way I actually learned how to do this, is that to try to fill in all the units first, because it goes in the same pattern every time, if you hadn't figured out. So fill in the units first, and then it's easier to fill in the numbers. You know that G stands for go to the periodic table. I know the molar mass of water is 18 grams per mole. I looked that up. We have 2 times 1 plus 16, right, is 18. And then we have the mole ratio right here. You need an equation. So you have, it's the decomposition of water. So it's H2O decomposing to H2 plus O2 with some electricity. So that's, yeah. So there are 2 moles of hydrogen for every 2 moles of water. And then there are 2 grams per mole of that. And so we end up with our answer as 8.33 grams of hydrogen. All right. Have a good day.